Assalamu alaikum. Today we are going to discuss steady state error design via integral control. We already know how to design the controller and how to design the observer. So if the system is already designed for the controller and then we want to minimize the error, then we should introduce integral control. Whatever the existing finite error that we have, if we want to make it to zero, then we have to place a pole at the origin. So the design procedure is actually you design the controller, then you also have to insert a pole at the origin. So the already designed system that we have is this one. So this is your system integral that gives our x and x dot. Then we know that c times x is our output. So this is our output. And the state is having a feedback with our system matrix A. And then for the controller design, we have the state feedback that we have with the gain minus k. Okay, so this is already the existing system, and this is what was our input R. Now, to minimize the error, basically you have to introduce a feedback from the output that will give us the error. So the error signal that we are going to get, that has to be nullified with a pole at the origin, which is an integral control, and then also a bit of gain adjustment. So this is basically our new input that we are getting. Okay, so we should have a subtract our output from the input. In this particular design problem, we are doing the design specific to the step input, but this can be further expanded for other type of input. Okay, so this is the error signal, which is E. And since we have an integral, we can say that we have another state, and the state can be given as xn. And that also makes that our error will be simply the derivative of that one, that is xn dot. So since we have our system, and this system can be used for minimizing the error. Okay, so now we can go for the formation of the equation of this particular setup. And also, we have to be careful about the zero that has been introduced, whether we have to introduce a zero or not, because from the time domain analysis, the frequency domain analysis that we do in general in the Laplace domain, there we have seen that somehow introducing a pole at the origin relocates the root locus. So the state space design, whenever you're doing the designing, so we have to keep in track of the zero as well, whether we have to introduce some zero because of this pole that we have inserted in the origin or not. Okay, so let's start with the derivation. So our error, we start with the error. Error E is basically, which is our new state xn dot. equal to r minus y, and we know that y is cx. So we have to be careful about the notation that this is matrix, this is vector in general, but for simplicity, we can also sometimes avoid the notations. So now, if we try to write the state equation for this new system, the state equations, then what you're going to see that x dot equal to ax plus bu existing. And we have new state, that is xn dot will be equal to minus cx plus r, and our output is cx. So this is existing. So now from existing one, let's combine to find out the state equations. So x1, x dot, which includes x, maybe x1, x2, x3, the original system, with the new one, xn dot. We're just adding the new state variable with the existing one. And then this will give us the A0 minus C0 xn, the state variables, plus B u, B0 with u plus 0, 1 r. So where is our u actually? We have u here. Okay, so this is our u. So now let us write the output equation. So the output equation will be y equal to, just include the other variables, so c0 with our x and xn. Okay, so this is our new equation, and also we can see what will be our value of u. We can replace the value of u with the appropriate equation that we can obtain, and we can see that u is basically two signal. One is minus kx that is coming through this path, and also we have kexn. So we can write that u equal to minus kx state feedback, then k, which is another gain with your new state, that is xn. So now if we put the value of u into the equation, then what we're going to see is that x dot xn dot will be equal to a0 minus c0 xn plus b0. We have minus k and k with xn. Okay, so maybe a bit okay, so also we have 0, 1 r. Now do a bit of simplification that will give us a0 minus c0 xn plus, sorry, this was actually b. So minus bk and then bke 0, 0, x, xn plus 0, 1, r. So ultimately, what you're going to get is that x, xn is common here. So you can say that a minus bk, which is already designed one, the controller designed one. Then you have bk, which is the new component that is coming because of the pole that you have placed at the origin. Then you have minus C0, minus C0. This is our new, the A matrix or the system matrix more specifically. Then you have X, Xn plus 0, 1, R. So, and this is our state equation. State equation by considering by inserting a pole at the origin, and our output equation is C0 X Xn. Now, since the system type is increased, a pole is inserted at the origin, we can easily now find out the characteristic equation of the system based on this new system matrix. Okay, so we can find out the characteristic equation. That characteristic equation will help us. We have to compare that characteristic equation with our desired characteristic equation with desired location of the poles. And then from that one, we can easily find out what will be the value of K and Ke. So K is also a vector, so it can have multiple components based on your system type, systems order that will dictate the state variables, and accordingly the value, the number of the components in K. Now, whether you have realized or not, since pole is inserted at the origin, definitely your system type is increased. So whatever previously was your finite steady state error, that will be now become 0. And also the 0, we haven't considered the effect of the 0. So one of the easiest assumption is to place the 0 exactly where it was in our open loop system. So in the open loop system, wherever the 0, we have to place the 0 in the same location. And then also we have to validate whether our second order approximation, they are valid or not. So if somehow they are not valid, we have to figure it out. Either we have to introduce a pole 0 cancellation, or we have to assume that our higher order pole is far away so that it is not affecting the dominant second order pole. So validation is also required in this scenario because of the fact that in our frequency domain analysis, specifically root locus, we exactly know what is happening in the transient response because of our physical intuition of the system. So in this case, since everything is done in the equation, and until otherwise we simulate the result, we do not have any idea what is happening. So the validation of the pole, the location of the 0, and the effect of the 0 on our overall transient behavior needs to be taken care of. So that assumption we have to take, and then we have to validate whether we are obtaining the desired characteristic or not. So this is the relevant theory, and this example is specifically for the step input, which can be further increased for other inputs like ramp and parabolic. So let's conclude the theory part here. And the next session, we are going to see one example regarding to this theory, inshallah. Assalamu alaikum wa rahmatullah.